Good morning, class. I just wanted to finish the example I left off last time that we didn't get to do, but I had you guys copy it down. It's typed up now, but we wrote it down together. Um, and it's the one that involves something called Newton's law of cooling. It's similar to the ones we've seen before. It's the slight difference is this: Newton's law of cooling states that the rate of change of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So originally, we were looking at these situations where the rate of change, which we call dy dx, is proportional to y. That's what that's a differential equation we solved where we got y equals c times e to the kt. But now it's not just proportional to y; it's proportional to the difference between between the object's temperature and the surrounding medium. So it's proportional to the difference between y and I'm going to call it capital T for room temperature. So this is going to be a slightly different solution when we solve the differential equation. We're going to look at that in example 6. But the idea is the rate of change is proportional to the difference between let y be the object's temperature and the room temperature. All right, so in this example, we're going to let y be the temperature in degrees Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. So that's room temperature, 60 degrees. If the object goes from 100 to 90 in 10 minutes, how much longer will it take for it to decrease to 80 degrees? So what we need is a model for the situation. We have a differential equation. If I can get an equation of y, then we got a shot at solving this. So we need to solve this differential equation up here. So um, dy dx is proportional to the temperature, the difference between the temperature and the room temperature, which is 60. All right. Um, to solve a differential equation, we're going to collect all of our y's on one side and our x's on the other side. So what I'm going to do is multiply both sides by dx to get the x off of the dy side. And I'm going to divide both sides by y minus 60, which is going to get the y and dy terms together. So what we're left with is 1 over y minus 60 times dy is equal to k times dx. Now the job here is to integrate both sides. The right hand side is going to be an easy integral. The left hand side isn't actually difficult if you do a bunch of these, but I'm going to go through kind of the process of how to do it, and then maybe you'll see the kind of a shortcut as we go. But I knew if the function was just 1 over y, the derivative would be the natural log of y. But now it's 1 over y minus 60. Does that really change things? So I'm going to use u substitution here. If I take u to be y minus 60, then the derivative of y minus 60 is just 1 dy. So this integral is now going to become 1 over u, and that dy is going to be replaced by du. Now on the other side, the antiderivative of k, I'm using an x here. I'm going to actually go back and use t for time. Let's use t for time. dt. Um, and it doesn't matter, but I want to use t for time. So the antiderivative of k with respect to time is going to be some constant times t plus some constant. Okay? And now the antiderivative of 1 over u is the natural log of the absolute value of u. And that's equal to k times t plus c. Now I'm going to replace u with y minus 60. And I'm dropping the absolute value. The reason why I can do that is because the temperature in the situation, um, it starts at 100 degrees, goes to 90 degrees, and we want to find out when it's 80 degrees. In all of these situations, the temperature is going to be greater than 60 degrees. So if y is bigger than 60, a number bigger than 60 minus 60 is going to be positive, so I don't need the absolute value. Um, so now I can exponentiate both sides to get um, the y on the bottom floor, so to speak. So the natural log and e undo each other. So y minus 60 equals e to the kt plus c, which is the same thing as e to the kt times e to the c. And the reason why I did that is because e to this, a constant to a constant is just a constant. So this is y minus 60 equals e to the kt times some constant. Add 60 to both sides and we're done. So very, very similar to the exponential growth and decay problems, except this plus 60 is the slight difference here. So now that I have a function of y, let's see if I can answer this question of when is the temperature going to be 80. So it cools from 100 degrees to 90 degrees. So right when we start, when t equals 0, the temperature is 100. So let's see if I can solve for c. By the way, in these type of problems, c is not the initial value. That plus 60 is the reason why, and here we'll see it right now. Y equals c e to the kt plus 60. Now if y is 100 and t is 0, I can subtract 60 on both sides. And then we get 40 equals c. Now e to the this is e to the 0, which is just 1. So this is just going to be 1. In other words, c is got to be 40. So that's nice. So now we have y equals 40 times e to the kt plus 60. So the initial, not the initial value, but using when y equals 100, t equals 0, we're able to find what c is. Now, if I can find out what k is, then finding out the temperature is 80 is going to be just an equation where we solve for t. So using the other piece of information that the temperature is 90 after 10 minutes, y equals 90 when t equals 10. We're going to get 90 equals 40 e to the kt plus 60. Subtract the 60 on both sides. 30 equals 40 e to the kt. Divide both sides by 40, you're going to get 3/4 equals e to the kt. Take the natural log of both sides. The natural log of 3/4 equals, this whole time I forgot to put in that t is 10. So let me do that real quick. 10, 10, 10. So equal to the 10k. And then divide both sides by 10. And we get negative 0.02877. So now we got E and now we got K and C, and now we can actually build our actual model here. 40 e to the k, which is negative 0.02877 t plus 60. Now I just want to find out how long it's going to take for the temperature y to be 80. So if I replace the temperature with 80, this is all we have to solve. And if you could pause the video, you guys try solving it from here, because this is very similar to the ones that we did on that worksheet on the last class that I was in. But I'm going to go solve it now. So if you didn't pause it, you can listen. If you pause it, you'll see if you got it right. So subtract 60 on both sides. 80 minus 60 is 20. And then divide both sides by 40, you get a half. Natural log both sides. Get rid of the e. And then divide both sides by that negative 0.02877. And put it in the calculator, and we got about 24.09 minutes. So when will it be 80 degrees in about 24.09 minutes? An interesting thing about this type of problem is it's got a couple of applications other than just finding out how objects cool over time. I remember doing a problem where, like, an investigator finds a dead body, and based on the body's temperature and the room temperature, you can find out how long the body's been dead for, so you can find out kind of the time of death using Newton's law of cooling, which wasn't an application that I would have saw, but it was an interesting use of this. Anyways, that's it. So now you can finish the problems in this section.